Question number 22 from HCV Kinetic Theory of Gases. First of all, we have to calculate the mean speed. The mean speed, when no mean is specified, it automatically means the arithmetic mean speed. The arithmetic mean speed which is actually existing according to Maxwell-Boltzmann distribution for ideal gases, that is equal to root 8 RT by pi into m, where m is the molar mass. So that will be equal to root of 8 into R in SI units is 8.314. The temperature of the hydrogen gas is 300 Kelvin in absolute scale. Pi is 3.14. Molar mass. Now molar mass means mass of 1 mole. Mass of 1 mole. So for hydrogen you may be knowing that molar mass is 2 gram. But we can't substitute 2 gram here because that is in grams. So we have to write divided by 1000 to convert it into kg. So 2 into 10 raised to minus 3 is the molar mass in kg. So this V will be the answer for the first part, which is to calculate the mean speed. Now here what we have to assume in the second case. Second case is a hypothetical case. Actually it's not that all the molecules will be colliding at 45 degree only, but just a hypothetical case. Imagine if that was the situation, that all of these molecules are having one single speed, which is mean speed, and all of these molecules collide at 45 degree exactly. Then in that case, if that was really what was happening, then to create this much pressure, how many molecules should be colliding? So let's say this velocity is v1, that we have already calculated the mean speed, and here we have a wall and we have to find out how many molecules are colliding with 1 square meter. 1 square meter means unit area. With unit area of the wall, how many molecules are colliding? So let's say this molecule comes at an angle of 45 degree, and it is coming with that mean velocity that we have calculated, which is v1. And we know that in case of elastic collisions, angle of incidence is equal to angle of rebound. So this will be again 45 degree, and it will go back with the same speed v1. So if you resolve the initial velocity or just before collision velocity into components, you will get v1 by root 2 here, you will get v1 by root 2 here. But after collision, v1 by root 2 here, v1 by root 2. So this v1 by root 2 is there, which is parallel to the walls, which is this component here, that remains unchanged because there is no friction. Smooth wall we can say. And because it is elastic collision, so this approach velocity v1 by root 2 and the separation velocity v1 by root 2 will be same. So what is the change in momentum then of one molecule? The change in momentum of one molecule will be equal to, magnitude wise only, m v1 by root 2 into 2, because this v1 by root 2 which was in plus I cap right now, after collision it will become towards left, which means in minus I cap. So the change in momentum is double of mv1 by root 2. This is change in momentum of one molecule. What is the total change in momentum per unit time? So total change in momentum per unit time is equal to change in momentum in one collision multiplied by how many collisions are taking place per unit time. So m v1 by root 2 into 2. This is the change in momentum of in one collision, multiply by how many such collisions are happening per unit time. Let's call it x, and that is equal to total change in momentum per unit time, which is equal to rate of change of momentum. Now here we are calculating the number of collisions per unit time with unit area of wall. So this is change in momentum per unit time because of collision with unit area of wall. And if this momentum change is happening per unit time is like, you can call it a rate of change of momentum, because rate of change of momentum is change in momentum per unit time. So this rate of change of momentum is because of force from unit area of the wall, and this is the force from unit area of wall. Force from unit area of the wall will be equal to rate of change of momentum of those molecules which are colliding with unit area of the wall per unit time. Okay. And if this is a force from unit area of the wall, the force on unit area of the wall will also be same, and that is pressure. So pressure is equal to mv1 root 2 into the number of collisions per unit time with unit area of the wall. Now this v1 we have already calculated, and the pressure that we require here is 100 kilopascal. So 100 kilopascal means 10 raised to 3. Small m is the molecular mass, not molar mass. So molecular mass is 2 into 1.6 into 10 raised to minus 27 multiplied by the v1 that you have already found out, multiplied by root 2, and then you will get the value of x, which is the number of collisions per unit time with unit area of the wall.